Chapter 11 Force and Pressure. In the previous class, you have already studied how objects move. Do you remember how we can decide whether an object is moving faster than other? What does the distance moved by an object in unit time indicate? You know that a moving ball rolling on the field slows down. This ball may change its direction of motion. Do you know that what makes an object slow down or go faster or change its direction of motion? Let us recall some of our everyday experiences. What do you do in rainy season when your classroom door is jammed? In such situation, you may push the door with great force. If the door still does not open, you may call some other students to help you. All of you apply force to push. See, the door open. What is a force? What can it do to bodies on which it is applied? We shall seek answers to such questions in this chapter. Force: a push or a pull. Actions like picking, opening, shutting, kicking, hitting, lifting, flicking, pushing, pulling are often used to describe certain tasks. Each of these actions usually results in some kind of change in the state of motion of an object. Can these terms be replaced with one or more terms? Let us find out. If you carefully study the above examples, you will notice that the word force is defined as a push or a pull acting on a body. The direction in which an object is pushed or pulled is called the direction of force. In science, a push or a pull on an object is called a force. Thus, we can say that the motion imparted to objects was due to the action of a force. When does a force come into play? Let us find out. Forces are due to an interaction. Interaction involves two objects. In interaction, each object acts in such a way as to have an effect on the other object. Suppose a child is standing behind a stationary cycle, Fig. 11.2a. Will the cycle move due to his presence? Suppose the child now begins to push the cycle, Fig. 11.2b, that is, he applies a force on it. The cycle may begin to move in the direction of the applied force. Note that the child has to push the cycle to make it move. Figure 11.3 shows three situations that may be familiar to you. Can you decide who is pulling and who is pushing in these cases? In Figure 11.3a, both the boys appear to push each other while the pair of boys in Figure 11.3b are trying to pull each other. Similarly, the horse and the man in Figure 11.3c appear to pull each other. The boys in the two situations shown here are applying force on each other. Is it also true for the man and the horse? From these examples, we can infer that at least two objects must interact for a force to come into play. Thus, an interaction of one object with another object results in a force between the two objects. Exploring forces, let us try to learn more about forces. Have you ever seen a game of tug of war? In this game, two teams pull at a rope in opposite directions, Figure 11.5. Members of both the teams try to pull the rope in their direction. Sometimes the rope simply does not move. Is it not similar to the situation shown in Figure 11.3b? The team that pulls harder, that is, applies a larger force, finally wins the game. What do these examples suggest about the nature of force? Force is applied on an object in the same direction and to one another. Now recall what happened when you and your friend pushed the heavy box in the same direction in Activity 11.2. If the two forces act in the opposite directions on an object, the net force acting on it is the difference between the two forces. What did you observe in Activity 11.2 when both of you were pushing the heavy box from opposite directions? When a team pulls the rope pulls the team. This was Newton's third law. When both teams pull in opposite directions, they often don't exert equal forces. So, we learned that a force could be larger or smaller than the other or equal to each other. The strength of a force is usually expressed by its magnitude. We have also to specify the direction in which a force acts. Also, if the direction or the magnitude of the applied force changes, its effect also. Contact forces. Some forces act on bodies only when they are in contact with that body. Forces that act only when there is physical contact between two interacting objects are known as contact forces. Muscular force is the example of contact force. Muscular force. Can you push or lift a book lying on a table without touching it? Can you lift a bucket of water without holding it? Generally, to apply a force on an object, your body has to be in contact with the object. The contact may also be with the help of a stick or a piece of rope. When we push an object like a school bag or lift a bucket of water, where does the force come from? This force is caused by the action of muscles in our body. The force resulting due to the action of muscles is known as the muscular force. It is the muscular force that enables us to perform all activities involving movement or bending of our body. In class 7 you have learnt that in the process of digestion the food gets pushed through the alimentary canal. Could it be a muscular force that does it? You also know that lungs expand and contract while we inhale and exhale air during breathing. Where are these muscles located which make breathing possible? Can you list a few more examples of the force exerted by the muscles in our body? Animals also make use of muscular force to carry out their physical activities and other tasks. Animals like bullocks, horses, donkeys and camels are used to perform various tasks for us. In performing these tasks they use muscular force. Friction. Remind some of your experiences. If you kick a ball it rolls for a while and then comes to rest. Why is it so? Ride a bicycle. When the bicycle starts moving with a good speed, stop pedaling. What do you observe? A car or a scooter also comes to rest once its engine is switched off. Similarly, a boat comes to rest if we stop rowing it. Can you add some more such experiences? In all these situations no force appears to be acting on the objects, yet their speed gradually decreases and they come to rest after some time. What causes a change in their state of motion? Could some force be acting on them? Can you guess the direction in which the force must be acting in each case? The force responsible for changing the state of motion of objects in all these examples is the force of friction. It is the force of friction between the surface of the ball and the ground that brings the moving ball to rest. Similarly, friction between water and the boat brings it to a stop once you stop rowing. The force of friction always acts on all the moving objects and its direction is always opposite to the direction of motion. Since the force of friction arises due to contact between surfaces, it is also an example of a contact force. You will learn more about this force in chapter 12. You may be wondering whether it is essential for the agent applying a force on an object to be always in contact with it. Let us find out. Non-contact force. Force due to without interaction between two objects is called non-contact force. For example, a magnet can pull an iron nails from a distance. Magnetic force, electrostatic force and gravitational force are examples of non-contact force. Magnetic force. Does the magnet on the rollers begin to move when the other magnet is brought near it? Does it always move in the direction of the approaching magnet? What do these observations suggest? Does it mean that some force must be acting between the two magnets? You have learnt in class Virgin Islands that like poles of two magnets repel each other and unlike poles attract each other. Attraction or repulsion between objects can also be seen as another form of pull or push. Do you have to bring the magnets in contact for observing the force between them? A magnet can exert a force on another magnet without being in contact with it. A straw is said to have acquired electrostatic change after it has been rubbed with a sheet of paper. Such a straw is an example of a charged body. When a charged body exerts a force and another charges or uncharged body is called electrostatic force. A charged body attracts an uncharged body. A positively charged body attracts a negatively charged body and repels a positively charged body without coming in contact, thus it is a non-contact force. You will learn more about electric charges in Chapter 15. Gravitational force. Do you know that when you hold a ball up in the air, the mass of Earth allows the ball to fall to the earth? The force that causes an apple to fall downward from an apple tree. A coin falls to the ground when it slips off your hand. Have you ever wondered why it is so? When the coin is held in your hand, it is at rest. As soon as it is released, it begins to move downwards. It is clear that the state of motion of the coin undergoes a change. Can this happen without a force acting on it? Which is this force? Objects or things fall towards the earth because it pulls them. This force is called the force of gravity, or just gravity. This is an attractive force. The force of gravity acts on all objects. The force of gravity acts on all of us all the time without our being aware of it. Water begins to flow towards the ground as soon as we open a tap. Water in rivers flows downward due to the force of pressure. You have learnt in class 7 that strong winds during a storm or a cyclone can blow away even the rooftops. You also learnt that winds and cyclones are caused by the differences in air pressure. Do you know that is there any relation between pressure and force? Let us find out. Pressure can be explained well with the following example. Do you think why it is easier to hammer a nail into a wooden plank? It is because we apply a greater amount of force into a very small area of the screw head. In this case, the pressure is very high. Try cutting vegetables with a blunt knife and then with a sharp knife. Which is easier? Do you get the feeling that the area over which the force is applied, for example, the pointed end of the nail, plays a role in making these tasks easier? The force acting on a unit area of a surface is called pressure. Pressure equals force, area on which it acts. I now understand why potters place a round piece of cloth on their heads when they have to carry heavy loads. By doing this, they increase the area of contact of the load with their head is reduced and they find it easier to carry the load. A potter head. So, the pressure on their head is reduced and they find it easier to carry the load. Note that the area is in the denominator in the above expression. So, the smaller the area, larger the pressure on a surface for the same force. The area of the pointed end of the nail is much smaller than that of its head. The same force, therefore, produces a pressure sufficient to push the pointed end of the nail into the wooden plank. Can you explain now why shoulder bags are provided with broad straps and not thin strap? And why the tools meant for cutting and piercing always have sharp edges? Do liquids and gases also exert pressure? Does it also depend on the area on which the force acts? Let us find out. Pressure exerted by liquids and gases. The pressure exerted by a liquid depends the depth, height of the liquid and density of the liquid. Note that the rubber sheet has been fixed on the side of the container and not at the bottom. Does the bulging of the rubber sheet in this case indicate that water exerts pressure on the sides of the container as well? Let us investigate further. Can you now say that liquids exert pressure on the walls of the container? Do gases also exert pressure? Do they also exert pressure on the walls of their containers? Let us find out. When you inflate a balloon, why do you have to close its mouth? What happens when you open the mouth of an inflated balloon? Suppose you have a balloon which has holes. Would you be able to inflate it? If not, why? Can we say that air exerts pressure in all directions? Do you remember that? What happens to the air, the bicycle tube, when it has a puncture? The bicycle tube is a rubber tube. When we fill air into the bicycle tube, then the air molecule inside the tube collide with the walls of the tube and exert air pressure. We find that gases, too, exert pressure on the walls of their container. Atmospheric pressure, a layer of air called the atmosphere, surrounds the earth. As you know, air is also matter and has weight. The weight of the atmosphere exerts a pressure on the surface of Earth. This pressure is called atmospheric pressure. Its magnitude is around 100 kilopascals, 100 kilopascals, at sea level. We know that pressure is force per unit area. If we imagine a unit area and a very long cylinder standing on it filled with air, then the force of gravity on the air in the cylinder is the atmospheric pressure, figure 11.17. But, how large or small is the atmospheric pressure? Let us get an idea about its magnitude. When you press the sucker, most of the air between its cup and the surface escapes out. The sucker sticks to the surface because the pressure of atmosphere acts on it. To pull the sucker off the surface, the applied force should be large enough to overcome the atmospheric pressure. This activity might give you an idea about the magnitude of atmospheric pressure. In fact, it would not be possible for any human being to pull the sucker off the surface if there were no air at all between the sucker and the surface. Does it give you an idea how large the atmospheric pressure is? The force due to air in a column of the height of the atmosphere and area 15 centimeters by 15 centimeters, figure 11.19, is nearly equal to the force of gravity on an object of mass 225 kilograms, 2250 N. The reason we are not crushed under this force of gravity is that the pressure inside our bodies is also equal to the atmospheric pressure and balances the pressure outside.